Hello, everyone. Welcome to the afternoon session of the Lithium-Ion Battery Analysis Virtual Symposium. I'm Caroline Harancic, the Associate Editorial Director of Spectroscopy, and I'll be your moderator for this event. I would now like to introduce our next speaker of the day, Maximilian Ries. Maximilian Ries received his doctorate from Technical University Berlin in optical spectroscopy on semiconductors and nanostructures. He is now Business Development Manager, Advanced Molecular Spectroscopy for Europe, the Middle East, and Africa at Thermo Fisher Scientific. Due to his previous work as an application specialist for FTIR and Raman, he has broad knowledge in the application areas for spectroscopy methods, specializing in battery materials. Maximilian, thank you for joining us today. You have the floor.
Hello from Berlin, Germany to everyone. Thank you very much for the kind introduction. I hope you already enjoyed the previous sessions of the Lithium-Ion Battery Symposium. My name is Maximilian Ries. I'm a Business Development Manager for Advanced Molecular Spectroscopy at Thermo Fisher Scientific, and I have a PhD in physics with an emphasis on Raman spectroscopy of interfaces. Today I was asked to present you with the solutions that Thermo Fisher Scientific offers to serve the battery value chain with vibrational spectroscopy tools. And to prepare the playground for our instruments, we as the world leader in serving science, we need to understand the driving factors for spectroscopy solutions in the battery industry. And to compete in the battery business, one of the biggest challenges is to provide the best battery performance. So optimizing the material quality, fine-tuning the composition, and allowing only the best material to enter the production by quality inspection are, alongside R&D efforts, the first step to a healthy battery. In today's society, we use batteries all the time, everywhere. So this brings along dangerous situations when a battery cell fails. To assess safety risks and to find the right materials such as flame inhibitors, to counter the risks and to analyze the hazardous byproducts during a thermal runaway scenario, for example, these are important steps to guarantee a safe and user-friendly product. And last but certainly not least, cost-efficient solutions are the key to a successful and competitive product. So time-consuming production steps call for analytical tools to precisely determine the endpoints and to reduce the idle time. The rapid and efficient material screening helps to identify inferior materials and improves device performance. And if we look into the approximate total cost for the production of a battery cell that you can see here on the right side, we can see that the total costs are majorly comprised by the material costs. 20% roughly go into the production, but more than 70% goes into the material costs, and almost half of the material costs go into the cathode materials. Another 30% goes into the development and manufacturing of the anode and the separator, and the rest is going to the electrolyte, housing, and others. So if we look closer at the individual components constituting a lithium battery cell, I want to highlight where exactly vibrational spectroscopy can play a role. So if we start to look into the electrolyte, this is where the lithium ions are introduced into the battery. So typically we have lithium cells that are mixed with organic solvents, and we want to use vibrational spectroscopy tools to investigate the raw materials, the composition, impurities, degradation products, and also the water content. We go to the anode. The anode is the part that stores the lithium ions and typically consists of carbon-based materials that intercalate the lithium ions. Raman spectroscopy is the go-to technique when it comes to analyzing carbon-based materials. So you can learn basically everything. You can learn about the chemistry, you can learn about the physical properties, but also about the electronic properties in the carbon-based material. We go further, we are going now to the separator that separates the anode and the cathode. And typically the separator is comprised by or from a multi-layer polymer. So it can be either polypropylene, polyethylene, but it can also be based on cellulose or ceramic coatings. Once again, we can look with vibrational spectroscopy into raw materials, but we can also look at the interface quality and the layer thickness of the materials. Then the next point in our battery will be the cathode material. So this is basically based on metal oxides and lithium precursors, and many applications are offered for vibrational spectroscopy tools, from raw material investigation, like the binders, the different precursors that are used, the cleaning detergent, but also composition, homogeneity, and of course, the residual alkali and moisture content. The last active part inside a battery is the current collector. Since current collectors are commonly made out of metals, vibrational spectroscopy techniques are not directly able to characterize them. Nevertheless, the interface quality and also residues and contamination on the current collectors can be assessed. Now, let's look a little bit closer to the individual tasks. We will start with the QA and QC and the raw materials. And on the left side, you can see that I indicated the battery workflow and where we are currently. So the problem statement for QA/QC is pretty easy. We need a reliable method for rapid material screening to ensure a constant quality. Avoiding toxic chemistry is, of course, a plus. And the solution, therefore, is to use the selectivity and sensitivity of infrared and Raman spectroscopy tools towards different materials. You can see here two of our compact solutions for your lab. On the left side, you can see the Summit FTIR, and on the right-hand side, you can see the DXR3 Flex Raman spectrometer. And by comparing spectra of the materials, you can build calibrations, apply these calibrations to incoming materials, and easily compare between batches to see differences in the incoming materials. To make it even easier, Raman spectroscopy uses visible lasers, and visible lasers can measure through glass or transparent containers, and therefore can be used to avoid security risks and going with the benefit of embracing green chemistry, because you're avoiding bad chemistry methods, reducing costs, and saving time and assure material quality. In this slide, you can see the difference in the Raman spectra of various lithium salts. You can see how easy it is to differentiate between these salts simply by the different shape of the vibrational spectra. By referencing then the intensity of the characteristic bands to the amount of the material in a mixture of two components, for example, it is straightforward to calibrate a quantification method and apply it to whatever material goes into your production process. The instrument of choice here would be our DXR3 Smart Raman that you can see in a lab situation of one of our lithium refinery customers here. A similar approach can be used to assess the molar ratios of different lithium salts in solvents such as DMC. And if you need an instrument that can fit into a glove box to look at the chemistry of reactive materials, then probably the Summit FTIR is the choice and it's the instrument that you are looking for. Let's move ahead in the production of our battery cells and look how we can use vibrational tools for the analysis of slurries, electrolytes, and electrodes. The problem here are mainly to establish a homogeneity, to quantify the residual moisture, and to determine precise endpoints in the production steps to reduce the idle time. In the large planetary mixtures or extruders, inline solutions such as Raman and near-infrared spectroscopy are implemented more and more into the production line. Following the trends, for example, of binder and solvent bands and monitoring the levels of moisture, allow it to save time and money. Inline techniques also minimize sampling and increase the efficiency of the production step. And speaking of efficiency, near-infrared spectroscopy is a great technique to largely reduce the amount of Fisher titrations that you need to perform in order to investigate the residual water across the whole battery workflow. So I do not want to go into details about where and how water can interfere with different materials used in the process, but it can be a serious safety threat from, for example, binder clogging, and also become a monetary factor when we think about idle time in the slurry or electrode drying. State-of-the-art Fisher titration is a time-consuming technique and operator-dependent, whereas near-infrared spectroscopy only needs about 2 minutes per sample. The technique can identify 100 parts per million to a few percent, but it also relies on a very precise reference method. When safety needs to be measured, FTIR is an excellent tool for quantification of gas emissions during thermal runaway scenarios, as seen here in this fire from a laptop battery. On the one hand, of course, the heat itself is a serious threat, but so are as well the potential toxic gases that form during the thermal runaway. It is essential to analyze which gases and how much of these gases are produced in the worst case scenario. The amazing part of gas FTIR spectroscopy is that you can measure up to 20 gases in a single spectrum. It also allows you to measure high and low concentrations in the same spectrum because of the vast amount of different bands that arise from the gas rotational bands. By using this type of analysis, it enables you to find safer solutions for future battery generations. And naturally, when we are speaking of safer solutions for the future, we have to go back to research and development. And as you have already listened to a great presentation from Professor Buchberger earlier this day, I do not want to take a very deep dive into the possibilities for research and development. More or less, I want to showcase a few ideas and start with a Raman cross-section of an anode material. Using our inert transfer cell that you can see on the right-hand side, you can prepare the sample in an inert environment, for example, in an argon atmosphere, and then easily transfer the sample in this inert atmosphere to the microscope. In the camera image here, you can see the current collector running diagonally from the left to the right, separating two different anode material coatings based on graphite material. You can see a blue and a red part in this Raman map in the center part of the image, and you can see then on the right-hand side two spectra, a red spectrum and a blue spectrum, and these correlate with the different colors inside the Raman map. So it means simply that red color presents a material that is based on carbon black, and blue represents a material that is represented more by a spectrum that comes from a graphite material. So this allows you to use a very simple Raman map to tell you about the material and how slight differences in the spectrum can have a large impact, and how easy it becomes by using imaging technologies in order to explain the differences of the material to other persons. Raman imaging can also be used to study the change of the material versus time, for example, during a charging or decharging example, for example, with an electrochemical cell, as you can see here in the image. If we look into the spectra that arise during the charging mechanism, you can see that highlighted here is a heat map. So it simply gives you a color coding for high intensity, which will be red, or low intensity, which will be blue. And if you look into the spectrum on the right-hand side, you can see that there's a shift in these two spectra, and then you can see that there's also a shift of the red dot going to the left side in the heat map. And this shows you that during the charging cycle, an intercalation of the lithium into the graphite is occurring. And this is actually what's altering the vibrational properties or the vibrational resonance frequency of the graphite layers, and therefore the slight shift is explained. And this allows you to precisely determine when the intercalation happens and what are the effects of the intercalation. Another possibility to apply Raman spectroscopy in a time frame is to look at other changes, such as the phase change, for example, from an anatized titanium dioxide that is not lithiated to an orthorhombic titanium dioxide during the charging or decharging cycle. And you can see it here highlighted by the different colors, similar to the Raman map we have seen on the previous slide, where simply the colors represent the spectrum coming or characteristic for a different type of material. And Raman spectroscopy is very useful in combination with other methods. So you've seen it here for electrochemistry, but you can also apply it to materials, for example, with XRD results or with XPS or SEM. Another case that I wanted to highlight very quickly is the thickness of a separator, because this is a very nice way how to apply Raman spectroscopy to multi-layer polymers by using confocal Raman imaging microscopy. What you can see here on the right-hand side is a spectrum based on a correlation to a polypropylene or polyethylene spectrum that you can see on the left side. And you can see how easy it is with Raman spectroscopy to differentiate between polypropylene and polyethylene. So polyethylene, for example, has basically CH2 bands and a very small amount of CH3 bands. And you can see it if you look into this area or this spectral region between 3000 and 2500 wave numbers, that due to the amount of CH2 and CH3 in the polypropylene, there are more bands evident than for polyethylene. And what we did here for this measurement is we did a depth scan. So this is not an XY mapping, but actually this is a depth mapping where you did Raman line scan in the X direction. Then you went into the depth of the material. And by going into the depths, you can identify the different layers. You can measure the layers. And this is all in situ without any changes of the material. You just put the material on the microscope and you start measuring right away. And you get your answer on the thickness and the different materials used in the separator. Speaking, of course, of a battery value chain, we want to look also into the recycling of batteries. And the recycling market is pretty enormous. So you can see here the available battery material for recycling by source, and you can see how it will increase, of course, over time as we have more and more batteries. And when we look at the of the amount of money that we have per ton of battery, we can see the material value constitutes a huge part of it. And even if we take out all the extraction costs, we still have a margin that makes recycling profitable. But what does it mean for us being spectroscopists wanting to use vibrational spectroscopy tools for recycling? Well, basically recycling is just material refinement. And what it means for us being spectroscopists, it just means the value chain starts from the beginning. And this means that all that I've told you before can be applied once again. So with this, I would like to thank you for listening to this presentation. If you're interested in knowing more, please don't hesitate to ask and to contact me. Thank you very much.
Thank you to all of our speakers who participated in today's session. I want to take a moment to thank the audience for attending and participating in the afternoon session of this virtual symposium on lithium-ion battery analysis presented by Spectroscopy.